So welcome to the talk. The title of the talk is a subpolynomial approximation algorithm for graph crossing number in low degree graphs. I am Zihan, and this is based on joint work with my advisor, Julia Chuzhoy. Okay, so the graph crossing number is a well-known problem in graph theory and graph algorithms. The input is just a graph that consists of vertices and edges. And the goal is to compute the drawing of the graph in the plane with fewest crossings. Okay, so a drawing is basically a mapping that maps vertices of the graph to points in the plane and maps edges of the graph into curves that connecting the corresponding endpoints of the graph. Okay, and the crossing is basically intersection between the curves representing the different edges. Okay, so for example, if the input graph is K4, a click on 4 vertices, then this is a drawing of K4 in the plane, and this drawing has 1 crossing. Okay, and in fact, K4 is a planar graph, so we do know that it can be drawn in the planar way, so there's no crossing at all. And the crossing number of a graph is defined to be the minimum number of crossings in any drawing of G. Okay, and the computational problem of the crossing number is just to compute this number for every input graph, and also compute a drawing that achieves this number of crossings. Okay, so this problem is really a classic problem in graph theory and graph algorithm. It has a very long history. Okay. So it was first introduced by Paul Turing in the 1940s, and then has been extensively studied and has shown very connections and applications in other areas of math and computer science. Okay, so for example, it has relations with graph algorithms, graph visualization, VLSI design, incident geometry, etc. Okay, but despite all this effort, the many aspects of this problem is still very poorly understood. Okay, so especially from the approximation perspective, which is the perspective that we are going to take today. Okay, and another feature of this problem is that like the custom type of algorithm like LP-SDP just does not seem to work on it. And basically we need to work from first principles. So let's look at some previous work of this problem on general graphs. So for general graphs, currently there's no non-trivial approximation algorithm on general graphs. So basically all approximation ratio depends polynomially on the max degree of the graph, which can be as large as n. Okay, and on the other hand, the strongest hardness result is only APX hard. Okay, but we do have one beautiful result about the crossing number, which is this crossing number inequality, discovered independently by Ita, Shiv-et-al, Newborn Severity, and by Leighton. Okay, so this inequality says that as long as the number of edges is larger than 4 times the number of vertices, then the crossing number has to be of the order at least m cubed over n squared. Okay, so basically the message it conveys to us is that as long as the graph is relatively dense, the crossing number has to be very high. Okay, then actually the most interesting part of this problem is really when the graph has a low crossing number, and it depends on whether or not we can find the best drawing of it or approximately the optimal drawing of it that achieves this number. Okay, so therefore it's reasonable to look at some special case. For example, one of the special case that's been looked at in the past 10 years is low degree graphs, where the graphs have max degree bounded by some constant or some slowly growing function of n. Okay. So in this special case, the last 10 years has witnessed a sequence of results of this problem. So the negative result is still only APX hard. And for positive result, for a long time, the best approximation stays O tilde n approximation. Okay, and it was first proved by a celebrated paper by Leighton and Rao, and then some logarithmic factors are shaved off in some subsequent work. Okay, so recently, this O tilde n barrier is broken, and it was first improved to n to the 0.9 by a sequence of 2 papers by Chuzhoy, Malkovich, and Siridopoulos, and by Chuzhoy. Okay, and more recently, it was further improved to square root of n approximation by a sequence of 2 work by Kobayashi and Siridopoulos. Okay, and 2 years ago, this was like the square root of n barrier is also further broken by Chuzhoy by a paper by Chuzhoy, Mahabhati, and me. Okay, so we like further improve this 0.5 in the exponent by a little to 0.488. Okay, but the more important contribution of our previous work is that we provide a reduction from this crossing number on bounded degree graphs to another related problem called crossing number with rotation system problem. Okay, and what we show is that any alpha approximation for this new problem implies a O tilde alpha approximation for the crossing number on bounded degree graph. Okay, and the main result in our new work is that we continue this reduction and we look at the crossing number with rotation system problem, and we design an n to the little one approximation for it. So combined with our previous work, this implies an n to the little one approximation for the crossing number problem. Okay, so this is our main result. And what is this crossing number with rotation system problem? So let's look at the definition. It's a very similar problem. The input is not only the graph G, but also for every vertex, a circular ordering of its incident edges. Okay, so for every vertex, there's a circular ordering E1, E2, E3, E4 defined on these 4 edges. Okay, and the goal is to output a drawing of the graph with minimum crossings, and also the drawing has to respect the circular orderings on each of these vertices. Okay, so for this vertex, the image of this edges entering this vertex has to respect this ordering. So it should be either this ordering or the flip of it. Okay. So in particular, we just fixed the circular ordering, but not the flip status. Okay, so these edges can enter it in a clockwise order or a anti-clockwise order. Okay. So this is a definition of the crossing number with rotation system problem. And what was previously known about it? So in qubit graph, it can be observed that crossing number problem is just the crossing number with rotation system problem, because imposing a circular ordering on 3 elements while still allowing the flip is basically imposing nothing. Okay, so it's still just a APX hardness result. And for the approximation aspect, only n to the 4 approximation is known. Okay, so this n to the 4 approximation seems a little bit weird because in this crossing number with rotation system problem, we are allowed to have input graph as multi-graphs. Okay, so in particular, number of edges can be significantly larger than number of vertices, and this n is number of vertices. Okay, so the previous work shows that if the orientation, so the flip status, basically the circular, the counterclockwise or clockwise, is also given to you, then we can get a n to the O to the n to the 4 approximation for this problem. Okay, so our result is that we can compute a solution that has number of crossings at most n to the little 1 times the optimal number of crossings plus EG. Okay, so we allow ourselves to compare not only with OPT, but also the number of edges in this graph. Okay, so this is not rigorously a approximation for this problem, but combined with the previous reduction, it is sufficient to obtain an n to the little 1 approximation for the eventual crossing number with rotation system problem. Okay, so this is our result, and we will dive into the algorithm, the remainder of this talk. Okay, so the algorithm is simply a divide and conquer framework. So in particular, we divide the input graph into smaller instances and even smaller instance until we get small enough instance. And then for each of the resulting small enough instance, we run some trivial algorithm on it to find a satisfying drawing. And then we have a bottom up combining procedure. So basically we take for every instance, drawing of each of the sub-instance and combine them into a drawing of the instance. And we go bottom up all the way to the original instance and get a drawing of it. So in order for this divide and conquer framework to work out, 3 things have to be satisfied. Okay, so if we just look at one step of the divide, the dividing G into 3 sub-instances, G1, G2, and G3, then first OPT, the sum of OPT of them, has to be no more than, not much larger than OPT of G. Okay, and also the number of edges in each of these graphs, the sum of them is also not much larger than EG. Okay, because recall our theorem compares the number of crossings with both OPT and EG, so we need both this not larger than relation to hold. Okay, and also there has to be an algorithm that given for every G1, G2, G3 a drawing of them, combine them into a drawing of G, such that the number of crossings is no more than the sum of these crossing numbers. Okay, so as long as these 3 conditions hold, basically this divide and conquer framework can work out. And now here we have some flexibilities, this not much larger than we have hidden some factors in it, and that will be explained later. Okay, so let's deal with, let's say, each of these conditions in turn. But before that, let's first look at how the sub-instances should look like. Okay, So most natural approach is basically to find a cut in the input instance and delete these edges, and just the remaining two subgraphs that we get are just subinstances. This is the most natural approach to produce subinstances. But this approach has a problem, okay? The problem is when we want to combine the drawing of each of them into a drawing of the original graph G, we may encounter too many additional crossings. So in particular, if this is a drawing of G1 and this is a drawing of G2, in order to add the missing edges back, okay, so these are deleted edges, and when we create a drawing of G, we need to add the image of this edge back, right? So when we add them back, we basically need to link the two corresponding endpoints by a curve. And since we have no control of what their drawings are, linking this pair of endpoints may just create number of edges crossings in the worst case. And in the worst case, for every such edge, we may encounter just this many crossings. So eventually the cost of adding the edges back may be the number of cut edge times EG. And this is too much for us. We cannot afford. Okay. So basically, in order to get around of this issue, we need another way of constructing subinstances. So what we do is follows. So we still cut the graph open along a cut by deleting these orange edges. But after that, for each G1 and G2, we add a special vertex to it and add special edges connecting these cut endpoints to the special vertex. Okay, so basically we add this red vertices and these purple edges additional. Okay, so the claim is this resolves the combining the drawing issue. And why is that? So if we now take a drawing of new G1 and the drawing of new G2, and we want to combine them into a drawing of G, what we can do is follows. Okay, we take the drawing of G1 and the drawing of G2. Okay, so this is the drawing of G1, it's a drawing of G2 separately. Okay, we take each drawing separately, and also we make sure that in the drawing of G2, there's no red vertices, but instead all these special edges incident to these red vertices, they touch the boundary in the circular order. Okay, so this can be achieved just by carving out a small disk here and viewing this as the surface, outer surface. Okay, so what we do next is just connect the corresponding edges around an annulus region within this disk that contain the image of G2. Okay, so in this way. So basically, the red vertex image of the G1's drawing, just we carve it out and place a drawing of G2 in it, and just reconnect the corresponding edges to let their entire image be the missing edges images. Okay, so this is the way of combining the drawings. And actually, some crossing may just happen in this annulus region. And one technical part of this algorithm in this part is that we do recall that we have the freedom of defining the rotation here. Okay, so defining the circular order here. And what we are doing is carefully design rotations, sometimes make them identical, sometimes make them obey some specific laws, such that either when we are merging these edges images, we incur no crossing at all, or we have to incur some add some crossings, but the number of crossings, basically the cost of composing the drawings, can be charged to OPT of G. Okay, so in this case, basically this combining drawing is dealt with. Only we need a plus OPG term here, and which is okay. Okay, so this can be dealt with only at the cost that the subinstances need to look a little bit complicated by adding a new vertex and adding a special edges to it. Okay, so what about, so actually what we are doing is not just cut the graph into two pieces and create two subinstances, but instead we just decompose the graph into several subgraphs. And for each of the subgraph, we create a cluster-based instance. And in order to stick them together, we create another central instance. Okay, so this is called the base disengagement. It's just a generalize of the previous pages, cut it into two parts. So what we're doing is cut into many parts and simultaneously get subinstances. Okay, so this is how to deal with the composing the drawing issue. And now let's look at the how do we bound the summation of the OPT. Okay, so this is our graph, and this is the two subinstances that we get, and we want to show that OPT G1 plus OPT G2 is the most not significantly larger than OPT of G. Okay, so the idea is still to extract the drawing of G1 and G2 from the drawing of G. Okay, basically use the optimal drawing of G to get a good drawing of G1 and G2. Okay, so let's say that we can find a set of passes connecting this cut edges to some vertex in G2, such that these passes are edge disjoint in G2. Okay, so what we can do then is just delete the red part of the graph, but only keeping this images of these green passes in the picture. And then this, together with the left part, this gives us a drawing of G1. Okay, and we can do the same for G2. Okay, so it's clear that the number of crossings in this drawing is just the crossings incurred by these edges together with this edge, and the number of the same holds for the graph G2, the drawing we construct for it. Okay, so as long as the edges are disjoint, these crossings can be all charged to the optimal drawing. It'll be the optimal number of crossings in the graph G. Okay, so in particular, the idea is we use the passes of G to get the images of the edges in the special edges of G1 and G2. Okay, and in particular, we do not really need this passes to be edge disjoint, and low congestion routing will do. Okay, only the factor in the increase in the OPT is just slightly larger, but we can afford any sort of constant loss here. Okay, so this is one way of showing that OPT is bounded, but it requires certain property of the clusters. So what are the required property? It basically, if we just look at the right cluster, it basically requires that these cut edges, we need to be able to find a set of edge disjoint paths to route them to a single vertex inside, such that this passes has low edge congestion. Okay, so we can intuitively call it routing to a center property. Okay, so we do not have at hand a property that has been studied before just characterize this property, but we can have a weaker one. So routing to a center implies routing all to all. So basically, if we can route a unit flow from each of these edges to some vertex inside, then we can route all to all among these cut edges. So I'm not going into the detail of it, but sort of in terms of multi-commodity flow, max cut, this is what we usually call it, routing all to all. And we do have a characterization of routing all to all property, which is this boundary well linkness property. Okay, so we say a cluster is boundary well linked if for any cut, the number of edges across this cut is comparable with both sides of the out edges. Okay, so for in particular for this cluster, the number of edges going from A to B is larger than alpha times minimum of this out edges and this out edges, and this is called alpha well linkedness. Okay, so as long as the cluster satisfies the boundary well linkedness with small alpha, well, with large alpha close to 1 alpha, then it has the good routing all to all property. Okay, but what we'll be interested is in is the reverse also true? Okay, so we basically know that the cluster has to be well linkedness, but is well linkedness enough for us to getting a routing to a center property? And our answer is, in our case, sort of yes. Okay, so one of the main technical result of our paper is that for a well linked cluster, either we can find a random routing to a center, which is a random path set that route all these boundary edges to a single vertex, such that the congestion square is bounded by n to the little 1. Okay, expected congestion square. Or we can say something else about this cluster, which is also something good. Okay, so what we will be saying is OPT plus the number of edges in this cluster is at least the number of boundary edges squared. Okay, so what this means and why this is a good thing for us. So it's basically saying something like the trouble caused by this cluster can be taken care of by the cluster on its own. Okay, so what do we mean by trouble? So recall that when we composing two drawings, the trouble is when the annulus region may contain crossings. And in the worst case, every pair of boundary edges may cross once. And this creates a most boundary edges squared crossings. And this property is saying, okay, it creates at most this trouble, but this trouble is compared with OPT of the cluster and number of edges in this cluster. So it can be charged to OPT of it. So what we can basically do is just cut it along these edges and just focus on the cluster on its own as a subinstance. Okay, so if either we can find a random routing to a center, or we can certify that something else good has happened. Okay, and both let us just go smooth with the decomposition step. Okay, so here the expectation congestion square is bounded, and some remarks says, yeah, we would like to make some remark. On the one hand, if we just require congestion to be bounded instead of expected, then it's impossible to get, because the graph can be just a bounded degree and there can be just many edges. So routing to a center, some edge has to have large congestion. Okay, and if we want the expectation of congestion to be bounded instead of expectation of congestion square to be bounded, then this is simple, but it's insufficient for us. Okay, because if A path use one edge and B path use the other edge, and these two edges create a crossing, then this crossing may eventually be turned into A times B crossings, and only A squared plus B squared can bound it, but not A or B. Okay, so this is sort of main technical part, main technical contribution of our algorithm in this part. It basically says that, okay, well linkedness is enough for routing to a center. Okay, but recall that we cut the graph along this cut and we get G1 and G2, and we want to sort of this property to happen to both G1 and G2. So basically this cut edges, they not only need to be routable inside this cluster G2, but also routable outside of this cluster G2. Okay, but this is something we do not know again, because this is sort of routing to a center inside the cluster. We have shown it is well linkedness, but routing to a center inside and outside is sort of something like doubly well linkedness. And we do have an algorithm that give us well linked clusters, but do not have any algorithm that give us doubly well linked clusters now. And another main technical part of our algorithm is that we'll show that, okay, we do not really need this doubly well linkedness property. Well linkedness property are enough, but only at a cost, where the constructing subinstances and composing joins, the previous procedures that we have described before, need to be now much more complicated. Okay, and this is called the advanced disengagement in comparison to the previous basic disengagement. Okay, so we will not go into the proof of this theorem, but I will. So basically, this theorem says that this OPT bounds can be taken care of. Okay, and just a very quick illustration of how the advanced disengagement look like. So in the previous basic disengagement, we decompose the graph into several clusters, and for each cluster, we create a cluster-based instance by sort of contracting the outside world into a single vertex. Okay, and now the construction of the subinstances in the advanced disengagement becomes much more complicated. We allow ourselves to further decompose the outside world into parts and contract each part into a single vertex. Okay, so this need to be done in a very delicate way, and we are not going into detail of this. Okay. Just showing and just an illustration that advanced disengagement can be much more complicated than the basic one, and it is sort of the cost that we have to pay. Okay, so these two criterions are both satisfied, and now we need to satisfy the last condition. The number of edges is not growing by a lot, and in fact, in order for the divide and conquer framework to work out, we need to make sure that the number of edges in each of these instances is significantly smaller than EG. Okay, because this makes sure the depth of the divide and conquer approach is small enough. Okay, so we will just use like a standard algorithm for this part. So actually, we will be recursively doing the minimum balanced cut. Okay, so a balanced cut is a cut that partitions the cluster into two parts. Each of the parts contains at most 90% of the edges. Okay, and among all such cut, the one that minimizes the number of edges in the cut is the minimum balanced cut. Okay, it has been shown previously that it's a corollary by the it's a corollary of the planar separator theorem actually, that this minimum balanced cut has sides at most the square root of OPT plus delta times EG, where delta is the max degree. Okay, so this basically, if we play with the math a little, it shows that as long as the delta is not crazy, Okay, as long as it is less than EG over n to the little 1. So there's no single vertex that takes up almost all the edges as its incident edges. Okay, then either the OPT is comparable to EG squared, or the mean balance cut is small. Okay, so if this happens, it basically means that, okay, this graph, we can forget about it, because any drawing, any trivial drawing is almost the optimal drawing. Okay, any trivial drawing, we can ensure that every pair of edge crossing at most once, and this is approximately optimal according to this criterion. Okay, or the mean balance cut is small, in which case we can just cut the graph and recurse. Okay, without worrying too much about cutting too many edges, because the mean cut is small. Okay, and actually we cannot compute the mean balance cut because it's a NP-hard problem, and what we will be doing is approximate mean balance cut. So what we'll be really doing is recursively apply the approximate mean balance cut until each part becomes small enough, and then apply well-linked decomposition to get well-linked clusters, and then advanced disengagement to get the eventual subinstances. Okay, so recall that there's a condition that we basically, the max degree is not crazy. There's no single vertex that takes up almost all the edges. And in this case, our approach is apply the approximate mean balance cut and well-linked decomposition and get small clusters, and therefore, and then get use advanced disengagement to get subinstances. So if this condition does not hold, then we will need another completely different approach to deal with this. So in particular, we ask, are there high degree vertices highly connected? If no, we will find small clusters and flower clusters, and we use basic disengagement to get small clusters, and we use advanced disengagement to get subinstances. If the answer is yes, then we get a very wide instance with a pair of vertices with a lot of paths connecting them. Then we use a completely different approach called cycle-based disengagement to get subinstances. Okay, so this is just a high-level overview of like how we deal with the other case, and this summarizes the algorithm. Okay, so so to sum up, we construct a n to the little 1 approximation for the crossing number with rotation system problem, which combined with the previous result give us a n to the little 1 approximation for the crossing number on bounded degree graphs. And some future direction includes what we can, so if we can improve this n to a little 1, whether or not the polylog n is possible, or can we prove like a similar hardness result, polylog n. Okay. And what about the crossing number with rotation system problem? Okay, so we have shown that the approximation ratio between these two are within the polylog factor, but what is exactly the value? Is it polylog or have to be beyond polylog, like n to a little 1 is the best? So that's all I'm going to talk about today. Thank you very much.